Now that you have TensorFlow installed on your computer, in this video we are going to write code in TensorFlow and Python to recognize handwritten digits using deep learning. In the same series, there was a video called What is Neuron, where we use insurance dataset, and I showed you a simple neural network with one neuron. We'll discuss that insurance dataset, and I will show you how a deep neural network will look like, or how a neural network with hidden layers will look like for the insurance dataset. Then we will cover some theory on the handwritten digits dataset, and then we'll jump into coding. I will quickly refresh the concept that we went over in What is Neuron video. Here I have an insurance dataset where the person age and whether the person has an insurance based on the age is given. And we are doing binary classification. Basically, based on the age, we are trying to decide whether person will buy an insurance or not. And for this case, we saw that we can have a single neuron or a logistic regression where the first part is the weighted sum and the second part is the sigmoid function. And here 0.042 is the constant that I came up with from my machine learning logistic regression video. And once you have this neuron, you can give the age and it will tell you whether person will buy the insurance. If the value is more than 0.5, person will buy, otherwise he will not buy. And you can supply different ages and you can know the answer. This was a simple form of neural network. Now this had only one feature, which was age, but you can have multiple features such as age, income, and education, in which case your linear equation would look something like this. And your neural network might look something like this, where you are feeding the input features using the input neurons, and your output neuron is doing two-step mathematical calculation. Number one is weighted sum and the second one is sigmoid, and it is telling you if the person will buy the insurance or not. Your data set in real life will be even more complicated. It will have even more features. So let's say you have age, education, income, and savings. In this case, you can have a hidden layer in the neural network where what you can do is use age and education to determine the awareness factor of a person. Awareness meaning how much aware a person is to buy the insurance. Usually if the person's age is young, people think that they will not fall ill and they don't buy the insurance. As the person's age increases, he or she will buy the insurance. Similarly, if the person is, let's say, a laborer and his or her education is not much, the awareness tend to be low. Income and saving factor can define affordability, because sometimes person has awareness, but let's say person doesn't have an income or he or she doesn't have enough saving to buy the insurance. Then the person will not be able to buy the insurance. So there is affordability factor as well. And awareness and affordability can ultimately decide if person will buy the insurance or not. So this is an example of a neural network with a hidden layer. And these are the weights that I have shown here. Actual neural network will look something like this, where every neuron is connected with every other neuron in the hidden layer. This is the reason it is called a dense layer of network. Dense meaning every neuron is connected with every other neuron in the other layer. Now let's move on to our digits recognition data set. So I went over this theory for insurance data set just to give you an idea on the hidden layer. Now handwritten digits are something like this. This is the problem that we have solved in our logistic regression machine learning video. If you have not seen that video, I would suggest that you watch it so you get some context. We can define a very simple neural network for this, where we can feed an image into the input layer like this, and the output layer will have 10 neurons, because we are classifying an image into 10 different classes. Basically we have 0 to 9, which is total 10. And we want to classify an image as one of these classes. So if you feed, let's say, this image into your neural network, the output will have this kind of score. Now, since we are using sigmoid function, the output will be in between 0 to 1. Okay, so this 4 looks like 82%, it looks like 4. This is what it's saying. It's something like similarity score. 0.08% it looks like, or maybe 8% it looks like 3. Okay, so these are the score, but the highest score is with 4. That's why we'll say, okay, this image is the digit 4. Similarly, when you have number 2, you will see that out of these 10 neurons, number 2 neuron will fire. The fire means it will have more score. Now, the question is, how do you convert this image into input neurons? Because you have x1, x2, xn neurons, so you have to feed this image into neurons. So the question is, how do you actually supply this image to neuron? Because when you have insurance data set, you have clearly defined values such as age, income, education, etc., and you can directly feed it into your neural network. But image is little tricky. So for image, what we do is, it is ultimately a two-dimensional metric where each pixel is represented with a number between 0 to 255. 255 is white, 0 is black, and in between you will have numbers. So you can actually have those pixels as a two-dimensional array, something like this, where the darker region will have 0, this region is very bright, so it has 240, the maximum value will be 255, and you get a two-dimensional array for representing this image. And then you can supply that two-dimensional array and you can basically convert that into one-dimensional array. So you can flatten the array. So flattening means you're converting it from two-dimensional array to one-dimensional array. Here in the first row we have 7 zeros and then 8 0, and our ninth element is 87. So you'll count here. You have 9 0 and then 87, then 240 and so on. So you're just very simple, friends. Two-dimensional array to one-dimensional array conversion. And this is 7 by 7 grid. So this array will have total 49 elements, and then you can have 49 neurons in your input layer. So this 0 goes to x1, this 0 go to x2, and so on. The 87 will go to x9 and so on. And these values now can be propagated into this neural network, which has 10 output neurons. So this neural network doesn't have any hidden layer. It has just input and the output layer into it. Now the problem that we are going to solve, we will actually have 28 by 28 grid. Okay, and we will flatten it, so it will become 784 neurons in our first layer, and then you have the output layer. When we are writing code in Python and TensorFlow, we'll first try to solve it using a simple neural network like this, and then we will add a hidden layer and we'll see how the accuracy improves. I ran a Jupyter notebook command, and that will launch a notebook like this, where I have imported some necessary modules. We already installed TensorFlow, so TensorFlow I already imported, and from TensorFlow I also imported Keras, which will give me some convenient API to use. We are going to use handwritten digits dataset from Keras library, and that is something you can load using this particular line here. And what this will do is it will load the train and test digits dataset into these variables. So let's see how many samples we have. So we have in xtrain 60,000 digits images. Similarly in xtest we have 10,000 images. So this is a pretty good, like a big data set. Now if you look at each individual sample, that sample is a 28 by 28 pixel image, and the way it's represented in numbers is a simple two-dimensional array like this. So just a two-dimensional array. 0 means those black points, and 253 means 255 is white. So these are between 0 and 255 values. If you want to see how it looks really, you can use matplotlib library. So matplotlib we have already imported as plt, the pyplot, and we can, in that library there is a function called, let me just remove these lines, and if you press B it will create a new cell, and here I am plotting the first training image. So this is obviously 5. You can look at couple of other images. See, the second one is 0, third one is 4, but you can see these are like clearly handwritten digits. And if you look at ytrain, so ytrain, let's say ytrain in, let's say, see, this is 4 in at position 2. So now I can see at position 2 there is a number 4. So if you look at ytrain overall, it is containing a number between 0 to 9. See, I print the first 5 simple, and this is how it looks. So this is straightforward. Our data set is loaded now. Now what we are going to do is we are going to flatten our training data set, because we saw in the presentation that we want to convert this 28 by 28 image into this single dimensional array that will have 784 elements. So how do you flatten it? In pandas there is a function called reshape. So when you have xtrain, you can call a reshape function on it, and in the reshape you can say, okay, length of xtrain, that is your first dimension. So it has 2 dimensions. If you just do this xtrain dot shape, you will see the first dimension is number of samples you have, which is 60,000. Second and third dimension is each individual image. So when you reshape, you still want, see, in the reshape what you want to eventually get is this 60,000, and the second dimension should be 784. That's why I am saying length of xtrain, which is 60,000, and then 28 by 28. So it does something like this. Let me store that in a variable, and I will call is flatten, and when you print the shape of it, see, this is what I wanted, 60,000 and 784. You can similarly flatten xtaste as well, and xtaste looks something like this, and both are flattened now. So if you look at the shape of, okay, let's guess what will be the shape of xtaste flattened. Exactly 10,000 number of images, and 784 is the second dimension. Pretty good. And if you are looking at, let's say, first individual element, you see that we converted from this presentation, which was 2-dimensional array, to single dimensional array. Until now, all the code that we wrote is extremely simple. Now what we are going to do is we are going to create a simple neural network. Okay, so that simple neural network will look something like this. It has just 2 layers, input layer with 784 elements, output layer with 10 elements. And the way you create this in TensorFlow and Keras is you use Keras dot, okay, so you use Keras dot sequential. So sequential means I am having a stack of layers in my neural network, and since it is a stack, it will accept every layer as one element. So the first element here is input, but Keras has this API where you can say keras.layers.dense. Dense means all the neurons here in one layer are connected with every other neuron in the second layer. That is why it is called dense. Okay, so I'm creating a dense layer here, and see the input shape is what? 784. See, input is x1, x2, x3 to 784. So that's what I have, 784 here. And the output shape is 10. So this way you are defining both input and output layer basically. This is your output, which has 10 neurons. So 10 neurons are this, 0 to 9. And the input is 784 neurons. So that's what you're saying, input shape is 784. You need to specify the activation function, which is sigmoid. Okay. That's it. We defined our neural network, very simple neural network. And we are going to store that into a variable called model. And once we do that, we need to compile it. So in TensorFlow and Keras, this is something you have to do all the time, where you kind of compile that neural network and you pass bunch of arguments. So first one is optimizer. So I'm using Adam optimizer. You will have now a lot of questions. What is Adam? Why we are using it? Hold those questions till later point. In the later videos, we'll cover these optimizers. But optimizers allow you to train efficiently basically. When the backward propagation and the training is going on, optimizer will allow you to reach to global optima in efficient way. And the second parameter is loss. So loss function, if you follow my machine learning tutorials, especially, let me just show you. So if you go to YouTube, by the way, and if you just search for code basics machine learning tutorial, you see this playlist where in the linear regression tutorial, I have talked about the loss function. I use mean square error or MSE loss function. Okay. Here we are going to use sparse categorical cross entropy. So what this means is our output class are categorical because we have categories basically 0 to 9. We have like 10 classes in our output. And sparse means our output variable, which is yTrain, is actually an integer number. If it is one hot encoded array, you would probably use categorical cross entropy. And you can look at the documentation and find different type of loss. See, in TensorFlow, there are different types of loss. The one that we are using here is this sparse categorical cross entropy. If you click it, see, this is the string that we're using. One can use mean square error as well. So mean absolute error, mean square error. And if you want to use mean square error, you will supply this. And if you want to know more about mean square error and the loss, you can follow this linear regression tutorial. Also, you can follow this gradient descent tutorial where I have talked about gradient descent and cost function. I would highly suggest watching this because this will clear some understanding on how actually these algorithms optimize and how they reach the global optimum value for the equation. I'm also going to maybe cover some math later, but for now, I want to build a working neural network in this video. That is my goal. That's why I don't want to go too much deeper into these parameters. So hold your curiosity for some later time and we will look into these parameters in detail in future videos. And in the metrics, you are saying accuracy. So accuracy is my metric. When neural network is compiling, my goal is to make it more accurate basically. Okay. And then you can call model.fit. So fit is where the training actually happens. So you are supplying here the training set basically. Okay, so X train is flattened, Y train we did not flatten it because simple array, and epoch is like number of iteration for which your neural network is going to run the training. Again, all these parameters, optimizer, loss, metric, epoch, we will cover these in future in detail, so do not worry too much. Right now we just want to execute this neural network. So Keras is actually small. Okay, input shape is not defined, so input shape is this. When you run it, now it is performing the training. In each epoch, you can see that it is going through these samples 1875, and then at the end of this run it is measuring the loss and the accuracy, and you will notice that as the time goes the accuracy will increase. Now here in our case actually the accuracy came out to be really very low. So one reason that I'm suspecting that the accuracy here is very low, like 0.99 would be high accuracy basically. 1.0 will be like perfect, but we got 47%. So one thing I'm suspecting here is that our values are not scaled. Often in machine learning, you need to scale the values. Okay, so what I will do is I will try to scale them. Now, how do you scale them? The value, each individual value is in range 0 to 255. So if I divide this whole array by 255, it will be scaled from 0 to 1. So let me do that here. So after I load my data set, or just before doing this, I'm going to now divide it by 255. Okay, so if you can see in my X train, I see two-dimensional array values are between 0 and 255. Okay, fine. I'm now dividing it by 255. So it will divide each and individual value with 255. And when you do this, now you can see that, see 0.99, 0.98. So now the values are between 0 and 1. So I will just control enter and execute this code again and see what happens, because scaling is a technique that improves the accuracy of machine learning model. We saw in this particular machine learning tutorial as well that when you do scaling, it tends to improve the accuracy, and we are already seeing that here. See, in third or fourth iteration, we got 92% accuracy. So now we have 92% accuracy, which means our model is trained in a way that 92% of time it will make accurate prediction. Okay, let's try to evaluate the accuracy on a test data set, because when it is running training, it is actually evaluating accuracy on a training data set. Before deploying model to a production, we always evaluate the accuracy on a test data set, and this is how you evaluate accuracy on a test data set, and that is also coming to be same 92.68. So this model looks pretty good. It's a simple neural network. It takes less time for training. So what I'm going to do now is I will just do sample prediction, you know, just for fun. So I have X test flattened and I want to predict it. Okay, so this predicted probably all my sample images. So let me do this first. So I will do only prediction for only first image. So let me see what is my first image. My first image. Okay, the X test is flattened actually. So let me just print this. Okay, my first image is 7. I want to predict my first image. X test flattened. Okay, we are getting some error here. Okay, looks like I need to predict it for all the values, and I'll just store it in y predicted, which will be an array, and the first image should be 7. Okay, so let's print 7. Okay, so the prediction is coming out to be this, and it has 10 values, because what it is now doing is it is printing those 10 scores like this, 0.29, 0.07 and so on. So these 10 scores are printed in this array, and we need to look at the score which is the maximum. Okay, and to look at the maximum score in NumPy, so you see we imported a NumPy module here, NumPy as np, right? So in that there is a function called np.argmax. It will find the maximum value basically, and it will print the index of that value. So now it's coming to be 7. So this is your prediction actually. So see, it is predicting it to be really okay. You can try maybe some other sample. Let's try the first image. So first image is 2 here. Okay, the first one. Perfect. Good job, guys. First one, see, this is predicting really nice. Now if you want to get a feel of how your prediction look like, we looked at confusion matrix in the same machine learning tutorial playlist. So we will just build a confusion matrix, and the way you build confusion matrix is we imported TensorFlow as TF. In TF there is a module called math which has confusion matrix function, and I will show you exactly what confusion matrix is. So labels is basically y test. So this is your truth data, and here you want to supply a prediction. So y predicted. Okay, but this cannot be y predicted because this is expecting the real labels. You know, like y test, if you look at y test. Okay, let's look at y test. These are the integer values, and if you look at y predicted, these are whole values. So we need to convert this into like concrete class labels. So the way you do that is you will say y predicted labels is equal to, you will use list comprehension. Basically you want to call np.argmax for all the elements, and in Python you can create a new array out of existing array by running a for loop. For I in y predicted, you can say for each I you want to find np.argmax. So np.argmax I. Okay, and when you do y predicted labels, let's just print first 5. See, now I am getting the first 5 prediction, and you can see that first 5 predictions are actually matching with the first 5 truth data. Okay, so I will pass y predicted labels in my confusion matrix, and let's store this into a variable called cm. Cm is confusion matrix. It's not chief minister, by the way. Okay, now what is this exactly? Well, let's print this confusion matrix in some visually appealing way so that we can visualize it better. And I'm going to use Seaborn library. You can just look at this code. Basically, instead of this visualization, I'm having some fancy colorful visualization. That's all this is. And what this is telling you is 963 times the label was 0, and our model predicted it to be 0. So 0th prediction was correct 963 times. 1106 times it was 1, and our model predicted it to be 1. 9 times, like this 9, the truth was 2, but our model predicted it to be 1. So see, anything that is not in the diagonal, all these numbers are errors. And you see we have quite a few of errors. For example, look at 40 number here. So 40 times it was number 2, but our model said it is actually 8. So you can see all the errors. You can see how those errors are distributed using confusion matrix. It's a very good tool to evaluate the performance of your model. Now I'm going to copy paste the same model here, and then I will add a hidden layer into this. So as you add hidden layer, it generally tends to improve the performance. So what I will do here is this. See, my last layer doesn't need input shape, because whatever first layer it is connected, it knows how to figure out the input shape from that. Okay, but my first layer input neurons are 784, and here I need to specify number of neurons in my hidden layer. Now how exactly you can specify how many neurons you want? Well, it is short of trial and error. There is no like fixed thumb rule. There are some guidelines, but I'm just gonna start with some value which is less than input shape. So I will start with 100. In the activation function, I will use an activation function called ReLU. We will look into later videos what ReLU is. You guys already know about sigmoid. There are other activation functions such as 10H, Leaky, ReLU, and so on. We will look into those in details. Again, do not worry too much about this. As I said, my goal of this tutorial is to build a working model, and then we will look into details like, peeling the layers of the onion. We will peel all those layers in later videos. Okay, invalid syntax because I don't have comma. You will realize one thing, which is when you have a hidden layer, your neural network will take some more time to train, because now it has to do more computation. You can add more hidden layers here. I'm having just one hidden layer, but you can have more hidden layers as well, and you can figure out how the performance is going to look like. And once the model is trained, of course, we are going to evaluate the performance on test set, and test set shows 97%. This means 97.15% is my accuracy. When I did not have hidden layer, my accuracy was 92%. So you can see 92 to 97, it's a good improvement. And then what I will do is, I'm just using the same code base. Okay, same code base that I used to draw this confusion matrix. I'm just plotting the same thing here, and you will realize that the number of errors in this black boxes have decreased. The numbers in this diagonal, those numbers are increased. In a perfect state, you will have 0 in all these black boxes, and in the diagonal boxes you will have big numbers. That is a perfect state when your model is perfectly accurate and it's not making any prediction. But friends, life is not accurate. So in life you see these imperfections, and which is okay. Now, one thing I did not like personally is whenever I am building a neural network, I have to make this flatten array. But luckily, if you don't want to make this flatten array, Keras comes up with a special layer called flatten. So what I'm going to do now is I will use the same code base here. So Control C, Control V, Control C, Control V is your friend. Okay, and here, let's say I don't want to create flatten array. I just want to supply X train, Y train. How do I do that? Think about that for a second. There is a way called keras.layers.flatten. Yes. In that you can say my input shape is what? 28 by 28, because that's one image dimension, 28 by 28. In the second one, you don't need to specify input shape because it can figure it out on its own. This makes it simple. So this way you don't have to create a flatten array. And also I'll just say epoch 5, but you can make it 10 as well. Okay, so that's all I had for this tutorial. This code is same as the other one. It's just that I don't want to create flatten array, and that's why I added this thing. But accuracy, everything you'll get it to be same. Now what I want from you is this. So there is a little exercise for you all. What you have to do is just try different optimizer and different loss here. Look at the Keras documentation. You can just say Google Keras loss functions and you will find losses in Keras, or maybe TensorFlow loss functions, and you will find all these losses. So I want you to try different losses, different values of metric, different values of optimizer, also different values of epoch, and tell me if you can get more accuracy than 97%. You can play with some more hidden layers as well. Also try to play with different activation functions and tell me if you can get more accuracies. When you try different values of loss, you will also get stuck into errors. It will not work. And I want you to play with all those so that you kind of get an idea on what kind of issues you face, and those doubts I will clear in the future videos.